IBESS, Atmospheric Systems and Pollution Management Part 5, will examine the pollution problem of stratospheric ozone depletion as a result of the release of industrial gases, chlorofluorocarbons, also known as CFCs. Remember that the stratospheric ozone layer is a non-living renewable resource. The significant ideas are stratospheric ozone is a key component of the atmospheric system because it protects living systems from the negative effects of ultraviolet radiation from the sun. Secondly, human activities have disturbed the dynamic equilibrium of stratospheric ozone formation. And lastly, pollution management strategies can be applied at different levels. Pollution management strategies are being employed to conserve stratospheric ozone. Here is the outline of all the available movies in the unit called Atmospheric Systems and Pollution Management. Use this outline to find the movie you need for review. This movie is focused here. The movie focuses on stratospheric ozone depletion as a result of the release of industrial gases, primarily, but not exclusively, chlorofluorocarbons, also known as CFCs. When the stratospheric ozone layer is depleted by CFCs, harmful UV rays stream to the Earth's surface and cause harm to living organisms. You should remember these IBESS syllabus statements from parts 1 and 2. Most reactions connected to living things occur in the inner layers of the atmosphere, the troposphere, and stratosphere. Human activities impact the concentration of atmospheric gases, such as ozone, carbon dioxide, and water vapor. Changes in the concentration of these gases has significant effects on ecosystems. This movie looks at the depletion of stratospheric ozone as a result of chlorofluorocarbons released by human activities happening in the troposphere. The CFCs transfer into the stratosphere to accelerate the breakdown of stratospheric ozone. This slide should help you organize your thinking around the management of pollution. Take some notes. In terms of pollution, this movie covers stratospheric ozone depletion by pollutants, primarily but not exclusively chlorofluorocarbons, also known as CFCs. When the stratospheric ozone layer is depleted, diminished by the pollutants, CFCs, harmful UV rays stream to the Earth's surface and cause harm to living organisms. Before looking at the depletion of stratospheric ozone, let's understand stratospheric ozone. And here are two relevant IB syllabus statements. Describe the positive role of stratospheric ozone in the absorption of ultraviolet radiation. Describe the dynamic equilibrium of ozone destruction and reformation. Now, I want to say something at this point that plays itself forward. Work hard to keep separate stratospheric ozone and tropospheric ozone. Tropospheric ozone is a component of smog, and as such, tropospheric ozone is harmful to living organisms. Stratospheric ozone serves a positive role of removing, absorbing harmful UV rays arriving into the Earth's atmosphere from the sun. Again, keep these two ozone issues separate and clear in your mind. Stratospheric ozone is beneficial to living organisms on Earth, while tropospheric ozone is harmful as a part of smog. With this slide, I could be talking about the structure of the Earth's atmosphere, but instead I've also given you the composition of the Earth's atmosphere below as 79% nitrogen gas, about 21% oxygen gas, small amount of carbon dioxide gas, and there are small amounts of other gases. This is the last time I mention the composition of the atmosphere. Study this slide. You need to memorize these percentages. The first 10 kilometers of atmosphere is known as the troposphere. When flying in aircraft, you always fly in the troposphere, albeit near the top of the troposphere, and clouds form in the troposphere. From 10 kilometers above sea level to 50 kilometers above sea level is the stratosphere. Notice the ozone layer that protects us from harmful UV rays is in this portion of the stratosphere. In this graph, you can see layers of the atmosphere as a function of altitude and temperature. The troposphere, 0 to 10 kilometers above sea level, and I've marked where the planes fly and where the clouds are. The stratosphere is 10 kilometers to 50 kilometers. Work to remember the altitudes of each layer. The troposphere gets colder with an increase in altitude, while the stratosphere gets warmer with an increase in altitude. The ozone layer of the stratosphere absorbs UV rays, and this is what causes the stratosphere to warm as the altitude increases. Here is a similar diagram of the layers of the Earth's atmosphere, except that the units are given in miles, not kilometers, so be thoughtful. You can see the UV rays from the sun being absorbed by stratospheric ozone here. This is the important role of stratospheric ozone. This slide also mentions tropospheric ozone as a part of smog. Remember that while ozone, O3, harms organisms if they breathe it in the stratosphere, where no people live, ozone absorbs high-energy UV rays, preventing the UV wavelengths from reaching the Earth's surface. This graph shows ozone density as a function of altitude, and you can see that stratospheric ozone is most prevalent in the stratosphere from about 15 kilometers to 30 kilometers, with a peak of ozone density around 20 to 21 kilometers above sea level. Remember, commercial aircraft rarely go higher than 10 kilometers. This graph shows the wavelengths of light from the sun that are absorbed by ozone. Ozone absorbs wavelengths from about 240 to 280 nanometers. These are the high-energy ultraviolet wavelengths, and by absorbing these wavelengths, the wavelengths don't reach the surface of the Earth where they would harm organisms. Once again, this image shows the ozone in the stratosphere absorbing UV from the sun, which, as it says here, the UV would cause harm to living organisms. Now you might ask the question, why is there an ozone layer in the stratosphere? And the answer is that it is naturally there. So let's take a look at the dynamic equilibrium of ozone destruction and reformation. To form ozone, O3, you need O2, oxygen, and monatomic oxygen, O, as you can see here. Now, monatomic oxygen results from UV rays that break O2 into two atoms of oxygen, as we can see here. So if you have oxygen, monatomic oxygen, and O2, you can form O3, as happens in the stratosphere. This would be considered an input to the ozone layer of the stratosphere, part of the dynamic equilibrium of ozone formation and destruction. Remember, stratospheric ozone is a non-living, renewable resource. So if the stratospheric ozone layer is to remain in equilibrium, then for every input, as we saw on the last slide, there needs to be an output, and so there is. O3 ozone is broken down by UV into O2 and monatomic oxygen. This is the absorption of UV wavelengths that I've been referring to. This slide shows you the absorption of UV by ozone, and in turn, ozone is broken down. The absorption of UV by ozone, as seen in this slide, protects living organisms on Earth from the harmful, high-energy UV rays that would otherwise stream toward the surface of the Earth. So here is the explanation of why the ozone layer exists in the stratosphere. Remember, you need O and O2 to form O3. Very high in the atmosphere, the mesosphere, there is very little ozone because there is no O2. All the O2 has been broken down into monatomic oxygen by the numerous UV rays at this elevation above the Earth's surface. Near the Earth's surface, the troposphere, there are very few UV rays, so there is no monatomic oxygen required to form ozone. But in the stratosphere, there is enough O2 and enough O to form O3, ozone. As you know, this movie is about stratospheric ozone depletion. So how is the ozone in the stratosphere being depleted? The answer is halogenated organic gases, sometimes known as CFCs for short. One is seen here. These are the molecules that result in an accelerated rate of ozone breakdown. Remember the dynamic equilibrium. Dynamic equilibrium is about inputs and outputs. Halogenated organic gases increase the rate of breakdown of ozone, the rate of outputs. CFCs are remarkably stable, non-polar compounds that have a variety of important uses in industry, and I'll get to that later. But remember, when CFCs are released to the atmosphere, UV light breaks them apart, as you can see here, and the liberated chlorine ion, a very reactive ion known as a radical, will break down ozone. And that brings us to this IB syllabus statement. List the human source of ozone-depleting substances, including aerosols, gas-blown plastics, this would be styrofoams, pesticides, flame retardants, and refrigerants. Halogenated organic gases, remember that term, CFCs, originate from refrigerators, air conditioners, certain pesticides, soil fungicides, fire extinguishers, as well as aerosols and gas-blown plastics, styrofoams. Halogenated organic gases originate from industrial solvents, aerosol cans, refrigerants like air conditioners, and in the manufacture of packaging materials such as gas-blown foams. That's right, CFCs are all around you, but you didn't know they were there. Refrigerators, air conditioners, solvents, and CFCs are used in the making of styrofoam, foam packaging. CFCs are extremely useful, industrially safe compounds, but they have a downside when they migrate to the stratosphere under the influence of UV light. CFCs are released to the environment when refrigerators and air conditioners are discarded. Maybe you can already imagine a method to reduce the release of CFCs as a pollutant to the environment. Again, when CFCs are released to the environment, they transfer to the stratosphere, where UV wavelengths split off a chlorine radical, which will in turn break down ozone. Now, I've already mentioned the ozone equilibrium in the stratosphere, so it should make sense to you that if CFCs cause more ozone to be broken down than would naturally reform, the output would be greater than the input, thus depletion of stratospheric ozone. Can you describe the dynamic equilibrium of ozone destruction and reformation? So here's the next relevant IB syllabus statement. Explain how halogen atoms, chlorine, the chlorine radical from CFCs, increase the destruction of ozone in a repetitive cycle, allowing more ultraviolet radiation to reach the Earth. With this slide and the next two, let me present the chemistry of ozone depletion. Now, you don't need to know the detail of these three slides, except to understand the catalytic nature of chlorine's destruction of ozone. The IB syllabus uses the term repetitive cycle in reference to the catalytic nature of chlorine's action on ozone. The term chlorine is also in this syllabus statement. Pay close attention. A chlorine radical, indicated by this dot, reacts with ozone to form chlorine monoxide and oxygen gas. Ozone is destroyed. Then the chlorine monoxide reacts with a single oxygen atom to release the chlorine and form oxygen gas. Do you see the catalytic effect here? Chlorine, after breaking ozone into two molecules of oxygen gas, is ready to do it all over again. This is the catalytic nature of the repetitive cycle in the breakdown of stratospheric ozone. So here is the general catalytic relationship. The chlorine radical, represented by X here, is a catalyst, as it reacts with ozone to form XO and oxygen gas. Then XO reacts with oxygen, monatomic oxygen, to form more O2, releasing the chlorine radical to work again and again and again, destroying the stratospheric ozone layer. In summary of everything I've said over the last 6 slides, CFCs are released to the environment and migrate to the stratosphere. UV light in the stratosphere breaks them down and liberates a chlorine radical. The chlorine radical breaks down ozone into oxygen gas, more oxygen gas, and the chlorine radical is liberated with every cycle to repeat the cycle, causing ozone to decline in the stratosphere. If you prefer diagrams to chemical equations, let's start here. Chlorine and ozone react over a series of steps slightly different from what I presented previously to form chlorine and oxygen gas, and then the chlorine is free to work again and again and again. So here is a visual to understand the entire stratospheric ozone depletion story by the pollutant CFC. CFCs are emitted into the troposphere by human activities, and those CFCs transfer to the stratosphere. CFCs are broken down under the influence of UV light in the stratosphere, and chlorine radicals accelerate the breakdown of ozone in a catalytic manner. You can see that breakdown here and here, in a catalytic manner over and over again. With the depletion of the stratospheric ozone layer, harmful UV rays reach the Earth's surface. Take some time to study this slide. At this point, you should be able to explain how halogen atoms, e.g. chlorine from CFCs, increase the destruction of ozone in a repetitive cycle, allowing more ultraviolet radiation to reach the Earth. Ozone holes are areas where stratospheric ozone is very, very thin, and they were first recorded in the 1970s. And by 1987, the world had responded with the Montreal Protocol, which called for limiting CFC production and release. In 1984, ozone depletion had just started, but by 1997, significant depletion of the stratospheric ozone layer had already happened. But in 1987, the Montreal Protocol had been passed and ratified by more than 100 countries. The Montreal Protocol is arguably the most effective international agreement on the environment ever negotiated. In this graph, you can see the decline in the ozone layer over the Antarctic from the 1970s until the late 1980s. So let's review a little bit and make some connections to things we've already studied. Is the stratospheric ozone layer natural? What does stratospheric ozone do that's positive? Is it renewable or non-renewable? Yes, stratospheric ozone is natural, and it naturally absorbs high-energy wavelengths, UV wavelengths, protecting the Earth's surface from these wavelengths. The stratospheric ozone layer is a non-living renewable resource. Secondly, dynamic equilibrium, inputs and outputs before CFCs, after CFCs. Ozone is formed and broken down naturally in the stratosphere as a part of a dynamic equilibrium. The inputs are slow, but fast enough that the stratospheric ozone layer is considered renewable by the IB/ESS syllabus. That's the good news. The inputs and outputs had been in equilibrium until halogenated organic gases disturbed the equilibrium by increasing the rate of ozone destruction. And lastly, what depletes the stratospheric ozone layer? Halogenated organic gases, such as CFCs, deplete the stratospheric ozone layer. The next important IB syllabus statement is, state the effects of ultraviolet radiation on human tissues, including the incidence of cataracts, mutations during cell division, and skin cancer. UV rays, such as those absorbed by stratospheric ozone, can cause skin cancer, resulting from mutations during cell division. UV rays, such as those absorbed by stratospheric ozone, can cause cataracts of the eye. The effects to humans and animals of overexposure to UV radiation include DNA mutation, skin cancer, radiation blindness due to cataract formation, and damage to the immune system. State the effects of ultraviolet radiation on biological productivity, including damage to photosynthetic organisms, especially phytoplankton, which forms the basis of aquatic food webs. UV rays can reduce plant or phytoplankton productivity. The leaf on the right has been exposed to high UV radiation for a period of time. Phytoplankton, seen in the image on the right, are microscopic producers at the base of the marine food web, and these phytoplankton are less productive under high UV conditions. The effects to ecosystems of overexposure to UV radiation would be DNA mutation to all organisms, reduced photosynthetic production, specifically phytoplankton, reduced complexity in food webs, particularly marine food webs, and reduced biodiversity. And here is the next important IB syllabus statement. Describe methods of reducing the manufacture and release of ozone-depleting substances. And methods would include recycling refrigerants, alternatives to gas-blown plastics, alternatives to halogenated pesticides, developing non-propellant alternatives, alternatives to aerosols. Following the framework for pollution management, the first strategy would be to find alternatives to gas-blown plastics, alternatives to propellants, alternatives to the pesticide, fungicide, methyl bromide. Now, alternatives to CFCs are likely to be more expensive and may have their own negative impact on the environment, but alternatives to CFCs would reduce the release of CFCs to the atmosphere. But using less of the pesticide, fungicide, methyl bromide might mean more agricultural pests, reducing crop productivity. Halogenated organic gases originate from refrigerators, air conditioners, pesticides, soil fungicides such as methyl bromide, and fire extinguishers. Finding alternatives would be a first strategy in pollution management. Again, a first strategy in pollution management would be to impose a government ban on propellants or a reduction in the use of gas-blown packaging material or a reduction in the use of air conditioners with CFCs. CFCs from air conditioners and refrigerators could be recycled. This would be considered a strategy 1 as a change in human behavior and a strategy 2 as it limits the release of CFCs into the environment at the point of emissions. With respect to the first strategy of pollution management, we could find alternatives to traditional CFCs. For example, substitution of HCFCs for CFCs. The CF bond is more stable under UV, therefore it's less likely to release a chlorine radical, but the HCFCs are more flammable and more expensive. We could also substitute HFC for the CFC. The CF bond is even more stable, but HCFC is a stronger greenhouse gas. And that brings us to the next IB syllabus statement. Evaluate the role of national and international organizations in reducing the emissions of ozone-depleting substances. The Montreal Protocol of 1987 was arguably the most successful international agreement on the environment ever forged. The Montreal Protocol on Substances that Deplete the Ozone Layer of 1987 and the subsequent updates is an international agreement for the reduction of the use of ozone-depleting substances signed under the direction of UNEP, United Nations Environmental Program. National governments complying with the agreement made national laws and regulations to decrease the consumption and production of halogenated organic gas, such as chlorofluorocarbons. You can see in this graph that CFC production has declined worldwide following the 1987 Montreal Protocol, but China has not fully complied with the agreement and a black market for CFCs has appeared. Again, in this graph, you can see how dramatically CFC production declined following the 1987 Montreal Protocol. UNEP, the United Nations Environmental Program, has had a key role in providing information and providing and evaluating international agreements for the protection of stratospheric ozone, but not all countries have ratified the Montreal Protocol, and exemptions were provided to developing countries, and a significant black market in CFCs has sprung up as a result of the Montreal Protocol. Not all countries have ratified the Montreal Protocol, and exemptions were provided to developing countries, and a significant black market in CFCs has sprung up as a result of the Montreal Protocol. As a result of the Montreal Protocol, atmospheric CFC equivalents are here rather than here. Keep in mind that an illegal market for ozone-depleting substances persists and requires consistent monitoring. Strategy 1 in pollution management would be to find alternative technologies or changing behaviors that reduce the release of the pollutant. Strategy 2 would be regulating and reducing the pollutant at the point of emission by setting and imposing standards, or introducing measures for extracting the pollutant from waste emissions. Now, we have a variety of strategies to manage the use and release of CFCs. We have international agreements, such as the Montreal Protocol. We have alternatives to CFCs that are less damaging to the environment. They could be more expensive. We need to be monitoring and working to reduce the black market that has appeared for CFCs. And any agreements, whether they be national or international, must be ratified and enforced. IB students should know that United Nations Environment Program, UNEP, has forged international agreements, for example, the Montreal Protocol and subsequent updates, on the use of ozone-depleting substances. As well, you should know the relative effectiveness of these agreements and the difficulties in implementing and enforcing them. Think here about the black market that's come up, but also think about the significant reduction in CFC manufacture and release since 1987. And lastly, students should be familiar with what steps national governments are taking to comply with these agreements. And that brings us to the end of IBESS, Atmospheric Systems and Pollution Management, Part 5.